Hello everyone, I would like to present on guide wave testing on pipeline and its report. This presentation is focused on how to check guide wave testing report, whether it is generated manually or piezoelectric system. This presentation includes three main things. First, I will introduce the guide wave testing method, including its capability and limitations. Second, present the three key procedures in guide wave testing method. And third, summarize the importance of using multiple center frequencies in guide wave testing and plotting a detailed UT image of each indication and important range in the report. What are guide waves? Guide waves are ultrasonic waves that propagate along lengths of structure and guided by and confined in the geometric boundary of structure. Because the ultrasonic waves propagate along axial direction of pipelines through the wall, we can inspect a long range of pipelines for any defect in the pipe wall. This is a schematic drawings explaining guide wave testing on pipelines. Like other NDT method, the guide wave testing method is answering client questions: where is the defect and how big is it? The guide waves are generated using guide wave probe installed at 0 feet distance and propagate along axial direction of pipelines. Once there is any change in the impedance in the pipe wall, such as a corrosion defect or well, the waves are reflected from them. We report the findings reading x-axis for distance and y-axis for amplitude after calibration. Now let's talk about how to find the defect in guide wave testing. Many people are not familiar to guide wave testing method and they think that the guide wave testing is different from the ordinary UT inspections, but it is exactly the same. Why so many people misunderstand it? It is because many inspectors did not report the detailed ultrasonic image of each indication and the local range of pipelines. Let us talk about how to find the defect in the guide wave testing data in the local range. This is one example of guide wave testing. Three data plots are shown: the rectified RF data in the blue color, video data with the magenta color, and the spectrogram plot for showing frequency spectrogram of each indication. We found these two defects at 2.4 and 2.8 feet. For finding indications, we use the signal-to-noise ratio as shown in the plot. This is a noise amplitude and this is a signal amplitude. If it is higher than 2, we mark as an indication. The spectrum plot is used for checking the frequency spectrogram of each indication. Now let us compare guide wave testing and ultrasonic testing method. Both methods are the same in finding defect in the pipe wall using ultrasonic image of reflected waves. The main difference is coverage as shown in the schematic drawings. The coverage of two methods are marked using red solid lines. The guide wave probe has two kinds. One is an encircling probe and covering whole pipe circumference. That includes MSS encircling probe or discrete piezoelectric belt. These probes cover the whole pipe circumference and generate ultrasonic wave along axial direction of pipelines. On the other hand, the MS sector probe covers only section of pipe circumference and generate ultrasonic wave along axial direction of pipelines. This sector probe is excellent for accurate inspection of 16-inch OD and bigger diameter pipe, press vessel, and tank inspections. The conventional UT probes such as PAUT and shear wave testing covers only local spot under the probe and near the probe. The inspection range in the guide wave testing method is more than 100 times that of the ordinary UT inspection. Let us talk about the capability and the limitation of a guide wave testing method. The capability of guide wave testing has several items. First, rapidly provides comprehensive condition information of a large area of structure. Second, require minimal preparations, insulation removal, scaffolding, excavation, coating removal, etc. Because the guide waves propagate along the pipelines, the installations need to be removed at only the probe locations. Third, inspect the inaccessible area remotely, and fourth, pinpoint where to do user quantitative follow-up. And fifth, enhance overall inspection efficiency by reducing time and cost. This is the main merit that facilities select the guideway testing method instead of other NDT methods. The limitations are as follows. First, it is a screening tool requiring quantitative follow-up inspection using other NDT methods. Second, it gives a rough estimate of remaining wall loss with a defect shape assumption. Now let's talk about the three key procedures in guideway testing method. The first procedure is generating ultrasonic wave in the pipe wall using coupling and acquiring data with equipment and the software operation. The second procedure is the propagation of ultrasonic wave and their interaction to geometric feature and defect. Once the ultrasonic wave is inserted in the pipe wall, the attenuation and the reflections are decided on the nature phenomenon. The only thing the inspector can control is using multiple center frequencies for finding more defect and better estimate the defect size. The details are explained later with the relationship between percentage cross-section area and the percentage reflection coefficient. The third procedure is generating report using software. It includes calibration of velocity, amplitude, and attenuation. Report the findings with a summary table and detailed data plots. The purpose of guideway testing report is delivering permanent record of tested pipelines with ultrasonic and visual testing results. This slide shows the first procedure of generating ultrasonic wave in the pipe wall. The guideway equipment generated a tone-burst electric signal into magnetosensitive or piezoelectric probe for deforming it. The local deformation in the probe is coupled to the pipe wall through one of the three couplings of shear couplant, dry coupling, or epoxy bonding. The coupled local deformation on pipe wall propagates along the pipeline as the guide waves. The inspector operates guide wave testing software for inserting pipeline information and acquiring ultrasonic data received in the guideway probe. This slide shows the second procedure of interaction of ultrasonic wave and defect. This nature phenomenon is the main reason of using guideway testing method for pipeline inspection because the nature phenomenon is the same regardless of inspectors and probe material of magnetosensitive and piezoelectric. In other words, the ultrasonic signal of a pipeline is not made by inspector, it is made by the nature phenomena. This schematic drawing explains the nature phenomena. Here are two things, several sizes of the ball representing different frequency of guide waves, and red half wall semicircle representing different axial lengths defect in pipe wall of gray color. The guideway testing method is simply rolling ball on the pipe wall and recording which ball loses momentum of the propagation due to the interactions. If the ball loses momentum of propagation, it is detected as a reflected wave in the guideway testings. The key point is that reflected signal changes depending on the relationship of ball diameter and axial length of defect, even though all defect has a 50% wall loss. This is one example of guideway testing of buried pipeline. The pipeline is 8 MPS Schedule 40, the fusion bonded epoxy coated pipeline. The photograph and the schematic drawing shows the encircling MSS probe installed using shear couplant, D1 defect location in plot and pipelines, and exposed range of the pipeline. 20 defects and indications were found with this guide wave testing. Most defects are located in the buried section of a pipeline. This is the guideway testing result. This pipeline has inspected using 5 center frequencies 32, 45, 64, 90, and 128 kHz. Many defects are found in the report. Are these a real defect? Yes, they are, because these defects are a result of a nature phenomenon. In the TCG, the time-corrected gain data plot, the background noise level does not go up and go down in the middle of the pipeline. The reflected signal indicates impedance change of a pipeline that is due to corrosion defect. D1 and D2s were verified using field testing. The inspection range and the number of indications varies at different center frequencies. 128 kHz has the longest inspection range, and 32 kHz the shortest inspection range in the buried pipeline. Found are 2 indications with 32 kHz, 5 indications with 45 kHz, and 19 indications with 128 kHz. With these results, we claim that operating multiple center frequencies increase the probability of defect detection and increase inspection range because some center frequency has less attenuations. Why does some frequency find more defect in pipeline? Now let us answer the questions with the result of guided testing project of US government that was performed in 2006 and 2007. As shown in the photograph, the defect was made by changing axial length, but its cross-section area is the same. The change of impedance along axial direction of pipeline is shown at the front and the rear end of the notch. This slide shows 128 and 32 kHz data are quite different axial lengths of the defect. The 128 kHz has a 1-inch wavelength, and 2 reflected signals are split with a 2-inch axial length notch. The 32 kHz data shows interaction of 2 signals even with a 4-inch axial length. This slide explains the wave interaction of front and the rear end of notch. This is ultrasonic wave interactions is the same phenomenon of Young's double-slit experiment of electromagnetic wave. The waves are doing the constructive interference if the path difference is equal to 1 wavelength. In guide waves, the path difference is equal to 1 wavelength if axial length of notch is equal to quarter wavelength, because the waves are reflected, the front and the rear has a 180-degree phase difference. This is a plot of reflection coefficient depending on the notch length and the wavelength. This x-axis of this plot is a normalized notch length with wavelength, and the y-axis is a percent reflection coefficient. This plot is very important because it is a relationship between percentage reflection coefficient and the percentage cross-section area. The plot shows experimental result with a test frequency of 32, 64, and 128 kHz. The solid blank lines shows the simulated result with the transmission line models. They are matching very well. The percent reflection coefficient is calculated with the ratio of reflected wave from the defect to instance wave at the defect location multiplied by 100. The percent cross-section area is calculated with the ratio of defect cross-section area to the total pipe wall cross-section area multiplied by 100. The percent cross-section area of defect is what the client wants to find, but we can only calculate the percent reflection coefficient from the reflected signal of guide wave testing. The reflected signal is ultrasonic image of defect. The cross-section area of defect is 6.44% because the increased notch length does not change the cross-section area of defect, but the percent reflection coefficient changes the notch length increases. It has maximum values when the notch length is equal to quarter wavelength. Then we can ask the following questions. What is a percentage cross-section area of defect? If we get the percent reflection coefficient with the guide wave testings, if you focus near the quarter wavelength location, we can see percent reflection coefficient is almost the same to percent cross-section area. As a screening tool, we assume that percent reflection coefficient is equal to percent cross-section area of defect if test is performed with multiple center frequencies. This table summarizes operating center frequency depending on the axial length of defect. If the defect is a half-inch axial length, 64 kHz has a maximum reflection coefficient. If the defect accumulates peeling corrosions, the axial length of peeling corrosion is smaller than 1/8. In this case, the high frequency of 120 to 250 is best for finding this kind of defect. Now we are back to guide wave data plot tested in 8 MPS varied pipelines. As we can see, there are indications on top of the signals. In this example, Q11 was detected at 45, 64, 90, and 128 kHz, but Q11 was written at 64 kHz because it is highest. Therefore, we can tell the Q11 defect is approximately half-inch, 0.5 inch long axial length. The percentage cross-section area of Q11 is calculated with the percentage reflection coefficient of 64 kHz data. We can conclude that guide wave testing should use multiple center frequencies, estimate axial length of defect, and the cross-section area of defect. Please ask inspectors how many center frequencies and what frequency they are using for guide wave testing. If they cannot answer it, they are not good inspector in guide wave testing. Now let's talk about the third procedure of generating report. The report is the most important thing because it should include all testing information, reference location with visual testing, and ultrasonic image of each indication and important range. MS Technology programmed the GIM software with the following 3 targets. First, the software should easily operate and less dependent on inspectors. To achieve this task, the GIM software has an automatic process of calibrating using pipeline drawing. Second, the GIM software can analyze up to 8 sets of data acquired at a different center frequency or 2 different locations in order to increase the probability of defect detections. Third, the GIM software generates ultrasonic image of each indication and important regions to prove the finding and give a permanent record of pipelines. The detailed UT image enhances the accuracy of guide wave testing and proves the long-range inspection with a detailed data plot. Now let us go back to the purpose of guide wave testing. It is finding defect and proves the finding with a detailed image. The top is a photograph of 4.5 inch OD pipeline and reporting one defect. The defect is Q15 is marked with red colored arrows. Can you see the defect in this pipeline? Client should ask a detailed photograph of defect. This is a plot of pipelines, not for defect that inspector is found. The bottom data plot is a guide wave testing result with a TCG data plot with a Q15 mark. We can see the Q15 signal, but it does not show the detailed UT image. Now we have 2 photographs, pipeline and defect. It is much better. The pipeline photograph and defect photograph are different. The bottom plot shows the guide wave testing result of 100 feet long pipelines. That is different from the detailed UT image of Q15. If we plot the detailed UT image of Q15 with a 4 feet length, the client clearly sees signal-to-noise ratio and the spatial resolution of Q15 signal and will be happy with the permanent recording of indication in the pipeline. This slide shows a guide wave testing report. The plot shows the 2 data plots generated using old MSS software. The data plot has x-axis range about 350 feet. The guide wave testing was started, another name of the long-range ultrasonic testing. The inspection report was made a long-range plot without showing detailed ultrasonic image. Because the report doesn't show detailed signal of indications, client check only table. Many UT inspectors do not believe on the result of guide wave testing because the report does not show the detailed UT image of short range. This slide shows the importance of detailed UT image in guide wave testing. In these days, the professional inspections are done with a detailed and clear image of ultrasonic X-ray, MRI, and photographs. Therefore, the guideway testing should show the detailed image of each indication along long lengths of pipelines if we want to claim that it is a large coverage inspection method. This slide shows what the MSS GIM software delivers a client in guideway testing report. The software reports a comprehensive image of rectified RF data, FFT plot, video plot, and spectrogram plot. The rectified RF plot of blue color and the video data plot of magenta color show the signal and the noise amplitude. The vertical red line in the spectrogram plot proves that the received signal are the fundamental torsional mode. The yellow line of the FFT result shows the frequency content selected indications. The comprehensive image of each indication enhances accuracy and gives permanent recording of tested pipelines. The detailed image allows any UT inspector to examine the test result by checking signal-to-noise ratio and the spatial resolution of each indication. The guideway testing also reports the visual testing result because the visual testing helps the client to see the report and check the indication location. It also verifies the findings, but visual testing result should be reported different color in the table and the plot. The MSS GIM software reported the visual testing result with a green color and VT for percent reflection in the table. In the data plot, the visual testing symbols are marked with a green dotted line, and the ultrasonic testing symbols are marked on the top of the detected signal. If inspection does not differentiate the visual testing and the UT testings in the table and the plot, it has a very high chance of the inspectors to do simply visual testing under the name of guideway testing. If client asks inspectors to report the detailed UT image for each indication and important range, the client can check whether the inspector is doing guideway testing properly. All defects are localized. What is wrong if a client asks for reporting detailed UT image in the long-range ultrasonic testing? Now let me summarize my presentations. I presented the 5 key items. First, the guideway testing method is a low-frequency ultrasonic testing method having large coverage. Second, enhance overall inspection efficiency by reducing time and cost. And third, acquire data using multiple center frequency for increasing probability of defect detection and estimating defect size. Fourth, it generates a report with a detailed UT image of each indication and important range for client to check the finding and to have a permanent record of a pipeline. And fifth, it reports a visual testing result that should be tabled and marked on the plot differently from ultrasonic testing result. Thank you for your attention. If you have any questions, please email me at skim@gwanalysis.com. Thank you. Bye.